drone, fighter jet, and helicopter, all in one. This is the future of American VTOL helicopters. At a time when world powers must be even more powerful, no military asset can afford to not be useful in virtually every mission. As a result, traditional helicopters must now make way for a more advanced type of aircraft, known as tiltrotors. They fly faster, farther, and most importantly, they have better VTOL agility. To understand the importance of VTOL in tiltrotors, it is important to know how it works. VTOL stands for vertical takeoff and landing, and as the name suggests, refers to aircraft that can take off, hover, and land vertically. The helicopter, Harrier jump jet, and F-35 Lightning II are some of the best-known examples, and they all achieve VTOL somewhat similarly. The task is to aim thrust downwards and take off from the reaction of an upward push. For the helicopter, its spinning blades create thrust like a large propeller, and this thrust is directed vertically. To move forward, the helicopter tilts slightly to direct some of its thrust forward, albeit slowly and inefficiently. For the Harrier, the aircraft uses a giant single engine with 4 thrust vectoring nozzles that can all aim thrust downwards during liftoff. Once liftoff is achieved, they're re-angled for forward flight, where the jet flies like, well, a jet. It's a similar case with the F-35B, except that the F-35B features 1 thrust vectoring nozzle instead, supported by a fan under the cockpit, which also provides thrust downwards. Once liftoff is achieved, the setup is reconfigured for the agility of a fighter jet. There are key takeaways here. The helicopter's spinning blades remain the most efficient and quickest VTOL setup, while the jet setup is the more agile in flight. With much to gain from both setups, tiltrotors combine both by featuring the spinning blades of a helicopter and engines that provide forward thrust while in flight. This is best understood by taking a look at the world's first production tiltrotor, the Bell-Boeing V22 Osprey. With one 3-bladed prop rotor, turboprop engine, and transmission nacelle mounted on each wingtip, the Bell-Boeing V22 Osprey is a half helicopter, half jet. Its default takeoff configuration is similar to the helicopters, being more hassle-free. During takeoff, the aircraft has its nacelles vertical and rotors horizontal. Once airborne, the nacelles rotate forward 90 degrees in as little as 12 seconds for horizontal flight, converting the Osprey to a more fuel-efficient, higher-speed fixed-wing aircraft. Most missions use fixed-wing flight 75% or more of the time, reducing wear and tear and operational costs, while allowing for longer-range line-of-sight communications for improved command and control. As helicopters do not have this option, the Osprey would begin to steal roles and missions from its yet-to-be-retired predecessors, particularly the Black Hawk medium-lift helicopter. In addition to that edge, the V22 Osprey is simply a better machine. It is over 170% faster with a top speed of 316 miles per hour compared to the Hawk's 183. The Osprey also comes with a significantly greater max range of 2,560 miles compared to the Hawk's 1,380 miles and flies as high as 25,000 feet, while the Hawk is limited to a 19,000-foot service ceiling. For a lighter weight, composite materials make up the Osprey's prop rotor blades and 43% of its airframe. However, the Osprey isn't all peaches and roses. For one, it cannot actually hover on one engine in the case of an engine failure. Also, if a prop rotor gearbox fails, that prop rotor cannot be feathered, and both engines must be stopped before an emergency landing. Then there are the poor auto-rotation characteristics due to the rotor's low inertia. To top it off, the engines produce so much heat that if installed on a ship, they could destroy the ship's flight deck and coating. These made clear the need for a new top-of-the-line tiltrotor for the U.S. military, one that would provide answers to the limitations of its predecessors, one that is known as the Bell V280 Valor. The Bell V280 Valor is a tiltrotor under development by Bell Textron in partnership with Lockheed Martin and a host of other reputable companies, including Lockheed Martin, Moog Inc., GE Aviation, GKN, Spirit Aerosystems, Eaton Corporation, Astronix Advanced Electric Systems, Israel Aerospace Industries, and Textron's sister company, TRU Simulation and Training. This all-star team became a necessity because the V280 was up against other contenders in the U.S. Army's Joint Multi-Role program. In 2013, the Army awarded technology investment agreements to Bell, AVX Aircraft, Karam Aircraft, and a Sikorsky Boeing team to develop the technologies and interfaces that would be integrated into the tiltrotor prototype. Each of these 4 teams received $6.5 million from the Army for Phase 1 of the program. However, with Bell, the developer of the V22 Osprey, once again up against Sikorsky, the developer of the Black Hawk helicopter, this competition would heat up pretty quickly and compel Bell to invest an undisclosed amount of its own money. In 2014, both of these teams would be chosen to continue to Phase 2 of the program, where the V280 from the Bell team and the SB-1 Defiant from the Sikorsky Boeing team would attempt to have a one-up over each other in providing a tiltrotor that's focused on the infantry squad and could handle much like a helicopter in terms of low-speed agility to have an unprecedented pitch, roll, and yaw response to those operations. The V280 was designed to achieve these and to push the limits even further by traveling twice as fast and twice as far as the current medium-lift helicopters in its size range. This translates to a cruising speed of 320 miles per hour or 280 knots, hence the name V280, a maximum range of 2,400 miles, and an effective combat range of up to 920 miles. These capabilities will prove all too vital, particularly for movement over vast areas like the Pacific. And according to the program director, one forward operating base of these aircraft could protect an entire country. As an upgrade from the V22 Osprey, the engines in the V280 remain in place while the rotors and drive shafts tilt. A drive shaft runs through the straight wing, allowing both prop rotors to be driven by a single engine in the event of engine loss. The V280 will have retractable landing gear, a triple redundant fly-by-wire control system, and a V-tail configuration. The V-tail structure and ruddervators made by GKN will provide high levels of maneuverability and control to the airframe. It will be made of a combination of metals and composites. The wings are also made of composites to reduce weight and production costs. Features in the interior include seats that wirelessly charge troops' radios, night vision goggles with 3D display, windows with 3D display, and other gear with, well, 3D display. These would give a world of comfort and ease of use to its crew of 4 and the up to 14 troops on board, who are all also treated to the feel of a familiar environment, as the fuselage of the V280 is designed to be visually similar to that of the Black Hawk. All of these will be thrust into the sky by a derivative of the Rolls-Royce T406 AE1107C engine used on the Osprey, which would be named the AE1107F. At the same time as increasing power from 5,000 to 7,000 horsepower, this new engine is a known element in tiltrotor aircraft with its 2 decades of prior use, lowering sustainment costs and decreasing risks of the project. Other V280 improvements over its predecessor, the Osprey, are lower disc loading, longer wings for greater hover and cruise efficiency, and a deal-sealing improved auto-rotation capability. Impressive as it is, though, the V280 must complete a checklist to seal the deal in becoming the US's next-gen VTOL. To keep pace with emerging threats, the next generation of VTOL vehicles must adhere to several foundational design principles, with 3 key ones taking the lead. Number 3. Modular open architectures. Future VTOL vehicles must have the flexibility to upgrade or replace the baseline systems with new technology as novel threats arise. This translates to the systems not being so permanently fixed to the airframe that modifications and upgrades are difficult or expensive to execute. Number 2. Resilient mesh network. Future VTOL vehicles must have advanced communications capabilities capable of exploiting all the connectivity options available across the radio frequency portion of the electromagnetic spectrum. And there isn't a much better way to go about that than a mesh network in which all potential players are instantly available through a seamlessly interoperable communications environment. This way, each asset can tap other sources for situational awareness and target information with the immediacy that only continuous connectivity delivers. Number 1. Manned-unmanned teaming. A core component of even 6th-generation fighters, manned-unmanned teaming ushers in a world of increased capabilities while reducing the risk to both pilots and higher-value assets. Simply put, much of the dangerous work in future airborne operations will be performed by unmanned systems. This capability will be even more decisive with the introduction of future drones, such as the V247 Vigilant. Also developed by Bell, the V247 is a large runway-independent Group 4 or 5 tiltrotor unmanned aerial vehicle designed to provide the widest array of support to ground forces while requiring less space to store and transport. With an unmanned tiltrotor like the V247 and a manned tiltrotor like the V280 working side by side, the sky is about to be the starting point for the U.S. military. Almost literally, but not quite yet, as there's one thing missing. To complete it, the U.S. military needs you to subscribe to this channel and give this video a like. Thanks for watching. See you in the next one.